Hello and welcome back to Calculus 1 section 4.5 on one of my favorites, optimization problem. They are not as favorite as the related rates, but they are holding the strong second place. Optimization problem. Important? Oh yeah, because we constantly want to figure out the most optimized way to do something, meaning min or a max. So you want minimum cost, you want maximum profit, you want maybe maximum surface area, you want minimum surface area, you want maximum volume, right? You want to minimize the surface area and maximize the volume that it encloses. What? Yeah, we'll see what that means. So all of these things, right, coupled with the cost, coupled with profits, coupled with all of these other things, to create a very, very useful section. Now, there are a lot of application in um, engineering here, but there is also a lot of application for business people because, optimizing the production and all of that stuff is very, very important if you are to run your own company, right? And remember what I said, what was the last class? Two classes ago, right? If you work for someone, then you make them money. If you own the company, then everyone who works makes money for you. They have salaries, but they still make you money. So the thing is that we would like to see what this concept is, and I'm going to start very simple with a completely pointless problem that says sum of two numbers is 18. Find the two numbers such that their product is maximum. So you want to figure out, right, which numbers that add to 18 would give you a maximum product. So we can just do the guess and check method, right? 1 plus 17 is 18. So here are the two numbers. And when you multiply 1 and 17, you get the product of 17. But then you also can do 2 plus 16, and that's also 18. And the product is 2 times 16, 32. Oh, that's much better, right? And then you have 3 and 15, whose product is 18. But when you multiply 3 times 15, you get 45. Oh, that's even better than 32. Okay, 4 plus 14, that's 18. And when you multiply, you get 52. No, you don't. You get 56. Well, that's even better. Okay, one more. 5 plus 13 is also 18. So that's product over there is now 65. So you see how it keeps rising. Keeps rising, going down, down, down. Is there a more efficient way to do this problem? Because I'm not going to sit there and try all of these combinations, especially if the numbers are supposed to add to 1075. I mean, yeah, I go ahead. So much easier way, faster way, would be to use mathematical functions and formulas and then use calculus because, hey, we're looking for maximum. Well, hold on, we know how to find max, right? That's a critical point when derivative is set to 0. So I just need some kind of function to differentiate. So let's see what kind of functions and equations I can write. Sum of two numbers is 18. Well, that should be common sense. sum of two numbers is 18. I don't really think that I need to discuss or talk about this, right? But then find the two numbers such that their product is maximum. So product of the same numbers needs to be max. And guys, you are done with your modeling. If you are able to take your word problem, whatever it is, and get this magic out of it, the rest is a very straightforward step-by-step way to solve it. So your main objective here is to learn how to transfer words into mathematical equations. Once you have these equations, it's literally game over, right? Now, why is the game over? Because you are going to have these two equations, the objective, and objective is the product is a maximum. That's the objective. And then you also have the constraint, because it's you have to get the maximum product with the constraint that these two numbers are adding to 18, right? Because can I just say 100 times 300 is going to be bigger than this? Of course it will, right? But these numbers don't add to 18, so they are not considered. So we are going to always have the objective equation, and we are going to have a constraint. So you are looking for the problem to have two equations, right, from your text. And now the procedure to solve this is always the same. Take your constraint, solve it for one of the variables. I don't care which one. Solve it for one of the variables, and then stuff that into objective equation, and you will have x times 18 minus x equals max. Max is some number, 10, 100, million, right? It's a number. So now, when you distribute this, this is what you have. And this is where you hit this with the derivative because you want to find the maximum. Now, remember what the maximum is, right? It will give you 0 in the derivative. Well, when you take the derivative of this, what do you get? You get 18 minus 2x equals 0. Derivative of the maximum is 0, because maximum is this number that we don't know, the product. But we don't care what it is now, because the derivative of whatever number you have there is always 0. So earlier, when we did not have any physical realm connected to these problems, we used to say, oh, to find min and max, set derivative equal to 0, right? Set derivative equal to 0. Now, you are actually computing it that should be equal to 0, because derivative of whatever this max number is going to be 0. And when you solve this, look what you get. X is 9. Well, that's cool. Bring that back into equation, compute that y is equal to 9. And we now know that the two numbers we were looking for are 9 and 9. Because 9 plus 9 is 18. And the 9 times 9 will give us 81, which the problem, the calculus, guarantees to be the maximum value for this problem. Now, we can go back to our list and say, okay, let's check that. So 6 plus 12 is 18. The product of that is 72, still going up. 7 plus 11 is also 18. The product in that one is 77. Then 8 plus 10 is also 18. The product is 80. You see how the gaps are kind of slowing down? And finally, 9 plus 9 is 18. The product is 81. And then 10 plus 8 is 18. And the product goes back down to 80. as I push. So now you see that I am going the other way. See, there is that max product. So we climbed all the way, but look what happened with the input numbers. They just swapped their spots. I already had 7 plus 11. It was just now 11 plus 7. This is the same calculation because multiplication and addition are commutative. So yeah, this problem is not that much of a big deal. It just introduces this very simple way of solving, where you come up with your two equations, and then you take the constraint, express a variable, plug in an objective, differentiate, and you immediately have one of the values. You go compute the other value and you move along. So most of our problems will have the identical way to solve it. Now, my favorite problems to this, is describe this in terms of let's make some money somewhere, is farmer problems. I think they call it farmer's dilemma or something. I say farmer problems. So farmer has 2,000 yard of fence. He wants to enclose rectangular plot of land of maximum area. Find the dimensions. Of the plot. You see, you don't just go in and start placing the fence, because you might have leftover, or you might need to go and buy more. So if you already have this amount of fence sitting out, you can go and use it, or you can compute what kind of a shape would maximize the area inside that plot of land. So rectangular plot, right? He definitely doesn't want to make a plot that looks like a star, right? And put the fence around it and then have a sheep go in there, right? That's not how you make a plot of land. Like, rarely you will find it as a triangle or something. Maybe there's a river going by, so whatever. You can find other shapes. But in general, it's some kind of rectangle, right? With lengths x, x, and y, y. And you want to put the perimeter fence so that maybe you can have sheep inside, right, or whatever. So farmer has 2,000 yard of fence. Well, that goes around the perimeter. So 2x plus 2y equals 2,000 should be the common sense to start with, because the perimeter fence goes on the perimeter of the rectangle, and the perimeter of the rectangle are 2x's and 2y's. So this is your constraint that you want to use for the perimeter. You want to use all of your 2,000 yard of fence. And you want maximum area. Well, that should be no-brainer as well, right? And when you divide here by 2, you have x plus y equals to 1,000 and xy equals to max. Aren't you going, hey, this used to be equal to 18, now it's equal to 1,000? Yeah, same thing. So all of these problems, guys, will work out this way, right? You will get your two equations, and then eventually you just have to solve them. Now again, solve for either x or y. No one cares. Plug that in. Multiply through. and hit it with the derivative to find the max. So the derivative is 1000 minus 2x equals 0, right? Derivative of max is 0. We talked about it. That max is the maximum area. I don't know, 300 yards squared, 300,000 yards squared. I don't care, right? It's a number. And whether I differentiate 3,300 or 300,000, it's always going to be 0. And from here, x equals 500 yards. And now when you plug that back into, when you plug that back into the equation here, you get that y is 500 yards as well. So you get a square, 500 by 500 yard. So think about it. This is a square, and you have 500 yard all around, and that's 2,000 yard, right? 2,000 yards offense. And we use it all, and the problem here guarantees the maximum area. Now, we actually have seen that it's going to be a maximum area because when numbers ended up being the same here, we had the maximum area. Now, is it a time for us to memorize that, the same number is the solution? Hell no. Here is the modified farmer problem. This is a river. All right. We can put some salmon in it. There we go. Salmon is now moving to the left. And we still have 2,000 yard of fence, and we want max area, but clearly we're not going to fence it towards the river because that river is going to serve as a fence on that side. So if you put sheep or cows or something in here, right, they might go and drink some water, but they're not gonna go and swim and look for the greener grass on the other side, right? There's enough green grass right here. So this changes, this configuration now changes my equation. You see, my perimeter is no longer 2x plus 2y. It's a single x plus 2y now. And you see that by looking at the picture. Right, look at it. You have x plus 2y equals 2,000, and you still want your area to be maximum because you want the maximum amount of land, right? So you can put as many sheep or whatever, right? It could be a garden, it could be orchard, it could be plot for the house, right? So you always want the maximum area that can be enclosed with this. So now, solve this in the same way. Well, you know what? Now I'm going to solve for x, just because. That's 2,000 minus 2y, and plug it in there. Because I just didn't feel like dealing with fractions. You can solve for y, right? You can get x over 2, and then 1,000. So it's not a end of the world. But if you can solve for x and avoid fractions, why not? So now you have 2,000 minus 2y, all of this times y, equals a max. Right? Because we plug that equation into our the product. And now you have 2,000 y minus 2y squared equals a max. And you have what? Now you have the derivative. Now please, use the head. We're taking out derivative in respect to y. You're trying to maximize y. in this case. So derivative in respect to y. Don't put d dx now when your variable is y. So we have 2000 minus 4y equals 0, right? Derivative of this maximum area, whatever it is. We could have calculated that area earlier, right? It's 25 and 4 zeros. Yard squared is the max area, right? So 250,000 right there. All right, so now we don't know whether this is going to be a 250,000 now, but whatever it is, the derivative of it is 0. And here is your set first derivative equal to 0 story from section 4.1 and 4.3, right? We did that a lot. So now you have that 4y is equal to 2000, and you get that y is equal to 500. Then you go, well, that's what we had before, right? Nothing changed. Yeah, a lot changed, because when you plug this in here, you will get that x is equal to 2000 minus 2 times 500. It's equal to 1000 yard now. So it's 1000 for x by 500 yard on y, and these are the dimensions. And if you multiply 1 times 5 and then 5 zeros, you see that your area is now doubled than what you had before, because obviously, right, you are using a river as a fence as well, so technically you have more fence. So all of this should make sense, right? So this is your max area now. So you have your answer that ended up being square, and then this new answer now here that ended up being a rectangle. Farmer's troubles continue. What if farmer needs to separate cabbage from rabbits and cabbage and rabbits from tigers, let's say? So creates these bins like this. Cabbage, rabbits, tigers. You can't mix these, right? You know what would happen if you put a couple of tigers with, with 100 rabbits. You wait 6 minutes and then you just have tigers, right? It's one of the funniest thing when they say the story of the Noah's Ark, right? And you put 2 of each animal in there, and you put the giraffes, and you put the zebras, and you put the horses, and you put the cows, and you put the sheep, and you put everything, and you put 2 lions, you put 2 tigers, and you wait 3 minutes, and all you have over there is like two lions and 2 tigers, and that's it, right? So the same thing goes here. You put these things together, so you want to separate, right? The farmer wants to separate these now. So I still have 2000 yard of fence, and now I still want to know the max area, right? Which means dimensions and then max area. So I have x, I have another x, and I now have 4 y's. Now I would like you to go through the entire process of computing this problem all the way to the end and see how does the dimensions change. So I'm just going to give you what? 2 minutes should be enough? 3 maybe? You're dealing with arithmetic over here.
I think I got it, Professor.
Okay, so what do you have for x value?
500 yards.
500. And how about the y?
250 yards.
250. Okay. All right, so it looks like it's um, significantly lower now, right? So we have 2x plus 4y equal 2000, and we still have xy equal max. Now I am going to divide here by 2 to reduce numbers. That's always helpful. Note that I'm always keeping these equations as a pair, right? Even though I haven't done anything to the max equation, I still keep it as a pair and I copy it. So now I get to write x equals 1000 minus 2y, and then we stuff that in here. 1000 minus 2y times y equals max. Distribute. And hit this with the derivative in respect to y to find the max. So that's 1000 minus 4y equals 0. And there is the y of 250. Nice. So now you take that and stuff it in your equation for x. And you get that x is 500 yards. So 500 by 250. Obviously the smallest overall area we had so far, because now you have to spend some of the fence for these middle parts, the two y's in the middle. From here, go ahead and keep making these problems, you know, geometrically as crazy as you want. You can have the river on this side and then have your fence with a bin. You can have your river on this side and have a wall of the nuclear power plant over here. So your plot of land is just this much. Right? So single x and a y, x and a y and a y, right? So you can literally make these situations, you can do this because maybe, right, you don't need everything. So that's x, that's y, that's x over 2, that's y over 2, right? And these things will come into the plane when you make that equation for perimeter fence, because every black line you draw is the fence part to consider. So it's really awesome to look at all of these problems. So make your own configurations. You can put the diagonal if you want to, and you will see how will it affect the area, because splitting it this way is not going to be the same as splitting it this way or splitting it this way. Now each one of these is split in half, but the length of the line that it's splitting is impacting the amount of fence you have for overall area. So it is really interesting to compare these three. Now again, for the students that are interested in this and learning and actually understanding this because they are planning on being engineers, clearly understanding these three examples here are very important, because and this is something that you can go and troll other people with, because splitting the rectangle each one of these ways splits the area in half, but then, right, it's different. Well, I'll let you figure it out. If you care about these things, go ahead and and figure it out. You can use the 2000. You can change it to 7 if you want. I don't care, right? But how are these different? So that's something like that. I want to jump into different type of problems a little bit, not just a farmer. Let's take a look at um, a box problem, or it's like a 3D problem where you want to have so packaging engineering, for instance, right? It's one of the branches of engineering. It was very important in the previous years where we used to ship everything, to import everything, right? So like almost everything that we have would be produced somewhere else, not in US. So packaging engineering was important because you have to import it, right? It has to travel across the world to get here. So designing boxes and designing packaging material is important, and sometimes you get to save a couple of cents when you design a box differently. Now you would say, well, who cares about a couple of cents? Like, why bother? Why would you hire someone? Well, yeah, a couple of cents, let's say 5 cents savings on one box times 100,000 boxes or 1 million boxes all of a sudden becomes a pretty penny. This is why you can never start the argument with a personal example or an example that you know of, because the world is much bigger than you, right? So yes, I understand that 5 cents doesn't mean anything to you. It doesn't mean anything to anyone personally, because you can't buy anything for 5 cents. But if you are making 1 million boxes and you get to save 5 cents for each box, that's a significant saving, right, for a company. So you have to be very careful about these claims. So now, what am I talking about? What I'm talking about, a box, right? That I want that box to have a particular volume, and because that's how much stuff I need to put in. Let's say it's a golf balls or tennis balls or literally anything. I don't care. Candles. I don't care what you're shipping. You just know that you need, you know, uh, 600 600 cube feet of volume, right? So need a box with a volume of 600 feet cubed and minimum surface area. That's what I need. This is the assignment that you get from your boss when you are working. And if you can't figure this out, out, right? We're going to hire someone who can. You don't get an example that says differentiate, blah, blah, blah. That's garbage. No one ever gives you that in a company. This is your problem. It came up at the meeting that they need to stuff 600 feet cube. This is how much the volume of whatever, apples or golf balls. I don't care what it is. Your job is to go make this happen on a paper so they can start producing those boxes, so they can start shipping and selling the product. If the company is not making money because of you, guess who's leaving, right? So let's go and make this. I'm going to have a box. Oh, I didn't say a square base. I'm sorry. Box with square base. I have to put that in, guys, because if I don't put the square base, then it's a Calculus 3 problem, and we're not going to deal with Calc 3 problems now. So I'm going to draw a rectangle and then say that the base is square by simply calling it x and x. So here's the box, and this box is supposed to fit 600 feet cubed. Now it's going to have some height y. I don't know what that height is yet. I'll figure it out. But the volume is when you multiply these three dimensions, so x squared y, and that has to be 600. So I already have my constraint. Volume is 600. Now, surface area. Well, this box has the top and the bottom. So the bottom is x squared. The top is x squared because the dimensions are x and x. And it has 4 xy sides. So area that we want to minimize is 2x squares for top and the bottom and 4 xy sides, which we want to be a minimum. Now, why do I want that to be a minimum? Can anyone tell me?
So you can save space if you're like packing it, I get. Like so you can
No,
sort of
space is
pack.
the volume.
Oh, right.
Yeah, why
So
do
you
I
don't
want the
have-
surface area? What is the surface area?
So you can use less material to make each box.
That's it. There's the business person right there. The least amount of surface area is the smallest amount of cardboard needed to make the box. And that's what you save the 5 cents I said. You save 5 cents on minimizing that. And when you minimize, guys, is no problem to make a box. Oops. To make, would 6 by 10 by 10 work? That would give me this much, right? It would give me the volume. I can just guess numbers. You know, 8 times 8 times whatever the hell is the third one. Divide 64 into 600, right? 9 feet something, right? So you can make the numbers up, but they are not optimizing the minimum surface area. You can go ahead and say, okay, 25 times 4 times 6. That's 100 times 6 is right? So here's the box. 25 feet long. Good luck with that. A 25 feet long box times 4 feet and then 6 feet high. It fits, right? So we want to create a box, and I have the volume as a constraint, and I have this one as the objective with the minimum, because my objective is to minimize the surface area so I can save money on designing the box, right? And the goal is to save 5 cents. That's perfect. On 100,000 boxes, we're happy. So what do I have? I have, from the top equation, again, y is equal to 600 over x squared, and that gets stuffed into this equation. So 2x squared plus 4x times 600 over x squared equals a minimum. That's 2x squared plus 2400 divided by x equals minimum. Are we all still here?
Yep.
Mentally?
Yeah.
Mentally? You know what I did in my algebra class? I used the polls and I put the question 1 plus 1 equals and put the multiple choice, see how many people answer it. To just see how many are not paying attention at all. Just put the zoom on and walk away. So, so now we hit this with the derivative. Always same steps. Get to equation, plug one into another, hit that with the derivative, solve the equation, and you're done. Okay, so derivative here is minus 2400 over x squared equal to 0. Derivative, this x is x to the minus 1, so that minus 1 drops and makes it a negative, and then minus 1 is minus 2, which drops it back into the denominator. So now I need to solve this equation. This equation is very easy because you just move the negative fraction to the right, becomes a positive fraction. And then you go and you cross multiply. That's a square That's a cube. Divide both sides by 4. And x worked out to be cube root of 600. Now, yeah, you can go and punch this in a calculator and get what the value is. But we don't care because we also know that y is equal to 600 over cube root of 600 squared. And now a little bit of basic algebra. That's a 600 over 600 to 2/3, which gives you 600 to 1/3, which gives you another cube root of 600 for y. And yeah, you got exactly what you were expecting. A cube. A cube with side A equal cube root of 600 feet. Everything was symmetrical in this problem. We did not have any problems with anything in terms of, and here are the modifications. Rectangular box of a square base and no top. That kills this too. And then your problem obviously changes calculation and you do not get the cube on the other end. Rectangular box with square base, with bottom and top, but the bottom is thicker material, more expensive. The top might be lighter material, so it's easier to open, right? There are so many modifications that you can put on that, and all of that stuff is changing these equations, right? So you figuring out equation from the picture is what is important. Now we'll have to stop here because it's 1:25. My office hours are starting in 4 minutes. I'm going to have a part 2 of this, and then we might push all the way through the derivatives next time. If you guys have any questions, my office hours, especially in the exam prep, even though I know you have those sample tests and stuff on my MATLAB to practice and the study plan. If you have any questions, please go to the Canvas, get the links and times for my office hours. Between now and the next Saturday, I'm having 5 hours of office hours, so, or including a Saturday, actually 6 then. With any questions you might have, your exam that you picked, exam 2, is on chapter 3, which are derivatives. And you absolutely have to have a problem on basic. You have to have one problem on the limit, h goes to 0. You absolutely have to have chain rule. You absolutely have to have product plus quotient.
What do you mean by basic again?
Basic, like derivative of x to the 7 is 7x
okay.
to the 6.
Okay.
Like, yeah. Trig plus inverse. And then for inverse, I said basically inverse tangent is the only one we care about. Log, differentiation, implicit, related rates. That's the word problems from 311. All of this tangent line equation. I probably missed something. Oh yes, I missed the problems with velocity and all of that stuff, the rate of change problems, velocity and acceleration and position. So position, velocity, acceleration problems. That was in the rate of change. Draw a derivative looking at the function. So you guys picked to have the exam next weekend. I am asking you to please join me in the office hours. You can go there right now. Just go to Canvas, get the link in announcements. If you have questions, and whether they are individual or group, right? Like problems and concepts, need to be able to write the formulas and for derivatives, the rules for derivatives. I think I covered everything, but again, there are 11 sections. 11 sections in chapter 3. So I hope you practiced it enough. I'll see you in the office hours if you have any questions.